Google account, Georgi Chipunov, Play Store, @intmain.in, main menu, Gemini, open menu for conversation actions, Pro. Conversation with Gemini, copy prompt, I'm coding a RTS engine, I need to code multiplayer, I want to add ordered packets, reliable ordered messages, September 15th, 2016 15 minutes read building a game network protocol. Hello readers, I'm no longer posting new content on gafarongames.com. Many people will tell you that implementing your own reliable message system on top of UDP is foolish. After all, why re-implement TCP? But why limit ourselves to how TCP works? But there are so many different ways to implement reliable messages and most of them work nothing like TCP. So let's get creative and work out how we can implement a reliable message system that's better and more flexible than TCP for real-time games. Different approaches. A common approach to reliability in games is to have two packet types, reliable ordered and unreliable. You'll see this approach in many network libraries. You might be thinking, oh of course, hash table, but there's a much simpler way. Constant buffer size equals 1024, UN32T sequence buffer size, struct packet data. Unfortunately, on the receive side packets arrive out of order and some are lost. Under ridiculously high packet loss, 99%. I've seen old sequence buffer entries stick around from before the previous sequence number wrap at 65,535 and break my ACK logic, leading to false ACKs and broken reliability where the sender thinks the other side has received something they haven't. The solution to this problem is to walk between the previous highest insert sequence and the new insert sequence, if it is more recent, and clear those entries in the sequence buffer to 0xFF. Now in the common case, insert is very close to constant time, but worst case is linear where n is the number of sequence entries between the previous highest insert sequence and the current insert sequence. Before we move on, I would like to note that you can do much more with this data structure than just ACKs. For example, you could extend the per packet data to include time sent, struct packet data, message create, int type, switch, type, case test message A, return new test messagia. Walk across the set of messages in the send message sequence buffer between the oldest unACKed message ID and the most recent inserted message ID from left, right, increasing message ID order. Never send a message ID that the receiver can't buffer or you'll break message ACKs, since that message won't be buffered, but the packet containing it will be ACKed. The sender thinks the message has been received, and will not resend it. This means you must never send a message ID equal to or more recent than the oldest unACKed message ID plus the size of the message receive buffer. For any message that hasn't been sent in the last 0.1 seconds and fits in the available space we have left in the packet, add it to the list of messages to send. Messages on the left. Older messages naturally have priority due to the iteration order. Include the messages in the outgoing packet and add a reference to each message. Make sure the packet destructor decrements the ref count for each message. Store the number of messages in the packet and the array of messages included in the packet in a sequence buffer indexed by the outgoing packet sequence number so they can be used to map packet level ACKs to the set of messages included in that packet. Add the packet to the packet send queue. On packet receive, walk across the set of messages included in the packet and insert them in the receive message sequence buffer indexed by their message ID. The ACK system automatically ACKs the packet sequence number we just received. On packet ACK, look up the set of messages it's included in the packet by sequence number. Remove those messages from the message send queue if they exist and decrease their ref count. Update the last unACKed message ID by walking forward from the previous unACKed message ID in the send message sequence buffer until a valid message entry is found, or you reach the current send message ID whichever comes first. On message receive, check the receive message sequence buffer to see if a message exists for the current receive message ID. If the message exists, remove it from the receive message sequence buffer, increment the receive message ID and return a pointer to the message. Otherwise, no message is available to receive. Return null. In short, messages keep getting included in packets until a packet containing that message is ACKed. We use a data structure on the sender side to map packet sequence numbers to the set of messages to ACK. Messages are removed from the send queue when they are ACKed. On the receive side, messages arriving out of order are stored in a sequence buffer indexed by message ID, which lets us receive them in the order they were sent. The end result. This provides the user with an interface that looks something like this on send. Test message equals, test message, factory create, test message, if, message, A equals 1, message, B equals 2, message, C equals 3, connection send message, and on the receive side, while, true, comma message equals connection receive message, if message, break, if, message, get type, equals test message, comma test message equals, test message, process test message, factory release, message, comma which is flexible enough to implement whatever you like on top of it. Next article, client-server connection. Hello readers, I'm no longer posting new content on gafarongames.com. Please check out my new blog at massbandwidth.com. Networking, related, sending large blocks of data, packet fragmentation and reassembly, serialization strategies. Reading and writing packets, state synchronization, enter a prompt here, open upload file menu, tools. Thinking, microphone, your IntMain chats aren't used to improve our models. Gemini can make mistakes, so double check it. Your privacy and Gemini opens in a new window. This is an excellent choice for an RTS engine. The text you provided is from Glenn Fiedler's Gaffer on Games, Reliable Ordered Messages, which is essentially the gold standard for game networking. For an RTS, specifically, this is superior to TCP because TCP halts everything when a packet is lost. Head-of-line blocking. Fiedler's method allows you to keep sending data while the lost data is recovered, preventing the lag spikes typical of TCP. Here is a breakdown of how to architect this specific system into your C++ engine, focusing on the reliability and ordering logic. 1. The core data structures. You need to distinguish between packets, the UDP blob traveling over the wire, and messages, the game commands inside the packets. The packet header. Every UDP packet you send needs this header to handle the ACKs. C++ struct packet header, UNT16T sequence. The ID of this UDP packet UNT16T ACK. The ID of the last packet we received from the UNT32T ACK bits. Bitfield indicating which of the previous 32 packets we saw. The sequence buffer. As the article emphasizes, do not use a STD, map or hash table. Use a rolling buffer for O1 access. You need this for two things. Tracking sent packets, to know what to ACK, and tracking received messages, to order them. C++ template. Type name T. Class sequence buffer. Static constant size equals 1024. Must be power of 2 for fast modulo UNT32T entry sequence. Size. T entry data. Size. Public. Sequence buffer. Initialize sequences to empty e.g. 0xff. Memset. Entry sequence. 0xff. Size of. Entry sequence. T insert. UNT16T sequence. Int index equals sequence percent size. Entry sequence. Index. Equals sequence. Return and entry data. Index. T find. UNT16T sequence. Int index equals sequence percent size. If. Entry sequence. Index. Equals sequence. Return and entry data. Index. Return nulter. You also need a remove function to clear old entries. 2. The logic flow. Here is the implementation strategy for the sender and receiver based on Fiedler's logic. The sender logic. Reliability. The core concept here is persistence. You don't send a message once. You queue it and include it in every outgoing UDP packet until you hear back that it arrived. C++. C++ class connection. 1. Packet tracking struct packet data. Bool act. STD. Vector. UNT16T. Message IDs in this packet. Map packet comma messages. Sequence buffer. Packet data. Sent packets. UNT16T next packet sequence equals 0. 2. Message tracking struct message data. Game message MSG. Bool act. Double last send time. To throttle sends if needed. Sequence buffer. Message data. Send MSGQ. UNT16T next message ID equals 0. UNT16T oldest on act message ID equals 0. Public. Void send game message. Game message MSG. Add to the message queue. Do not send via UDP yet auto slot equals send MSGQ insert. Next message ID plus plus. Slot. MSG equals MSG. Slot. Act equals false. Slot. Last send time equals -1.0. Void send UDP packet. Packet header header. Header sequence equals next packet sequence plus plus. Header ACK equals last received packet sequence. Header ACK bits equals generate ACK bits. Logic to inspect received buffer. Start Gaffer's algorithm 1. Create packet entry auto P data equals sent packets insert. Header sequence. P data. ACK equals false. 2. Fill packet with unACK messages. We iterate from the oldest unACK message forward. We fit as many as we can into the MTU. Usually 1400 bytes for. UNT16T ID equals oldest unACK message ID. ID. Next message ID. Plus plus ID. Auto MSG data equals send MSGQ find. ID. If. MSG data and MSG data. ACT. Serialize message into packet buffer. Add ID to P data. Comma message IDs in this packet so we can map ACKs later P data. Message IDs in this packet pushback. ID. 3. Transmit UDP packet socket send. Header. Payload. The ACK logic. Closing the loop. When you receive a packet from the client, you look at the header. It tells you what they have received. C++ void on received packet. Packet header header 1. Process packet ACKs check header ACK and header ACK bits identify which of our packets. Packet IDs they received. STD. Vector. UNT16T. ACK packet sequences equals decode ACK bits. Header ACK. Header ACK bits. 4. UNT16T packet the following. ACK packet sequences. Auto P data equals sent packets find. Packet the following. If. P data and P data. ACT. P data. ACT equals true. 2. Correlate packet comma messages because this packet arrived. All messages inside it arrived for. UNT16T MSG ID. P data. Message IDs in this packet. Auto M data equals send MSGQ find. MSG ID. If. M data. ACT equals true. We can now release the memory for this message. Update oldest unACK message ID by moving it forward until we hit an unACKed MSG. The receiver logic. Ordering. This is where you ensure the RTS simulation stays deterministic. You might receive message 5 before message 3. You must hold message 5 until 3 and 4 arrive. C++. Tick. You might receive message 5 before message 3. You must hold message 5 until 3 and 4 arrive. C++ class connection. Sequence buffer. Game message. Received MSG buffer. UNT16T next expected message ID equals 0. Public. Void process incoming UDP. Packet. Deserialize messages inside the packet for auto and MSG. Packet messages. Store specific message by ID if we already have it. Ignore. Deduplication. If received MSG buffer find. MSG ID. Received MSG buffer insert. MSG ID equals MSG. Call this every frame in your game loop void pump messages. While true. Check if the next ordered message exists in the buffer game message MSGPTR equals received MSG buffer find. Next expected message ID. If MSGPTR equals nullter, we have the next piece of the puzzle. Dispatch to game. MSGPTR. Next expected message ID ++. Else, we are missing a link in the chain. Stop processing. We must wait for the next UDP packet to fill the gap break. Why this is hard but worth it. Redundancy. If your RTT is 100 milliseconds and you send 60 packets sec, a single message might be sent 6 times before you get an ACK. This consumes bandwidth. Optimization. Only include the message if it hasn't been sent in the last X milliseconds, e.g., 50 ms. Bitpicking. You need a tight bit writer bit reader class. RTS units move efficiently. Sending 32-bit integers for every Boolean flag will kill your bandwidth. Next step for you. The hardest part of this implementation is typically the congestion control. Deciding how many messages to stuff into a packet without flooding the connection. Would you like me to write the generate ACK bits and decode ACK bits functions? The bitwise math. For you, that is usually the most error-prone part of the implementation. Yes, code in C++ the generate ACK bits and decode ACK bits functions. The bitwise math. Here is the C++ implementation for the ACK bit field logic. The logic concept. The ACK field represents the most recent packet ID we have received, e.g., 100. The ACK bits field, a 32-bit mask. Bit 0 equals ID 99. ACK 1. Bit 1 equals ID 98. ACK 2. Dot. Bit 31 equals ID 68. ACK 32. The implementation. I have included a minimal mock of the sequence buffer class so you can see exactly what methods are being called during the generation phase. C++ include. Xtint. Include. Vector. Include IOStream. Comma helper. Handling sequence number wrapping comma. This ensures that 0 is considered newer than 65,535. Useful if you need to check if a sequence is actually valid before processing bool sequence greater than UNT16T S1, UNT16T S2 return, S1 S2 and an, S1, S2 equals 32,768, comma S1, S2 and S2, S1, 32,768, comma mock sequence buffer, for context, comma. You should already have this from the previous step. We only need the exists. Method for the ACK logic class received packet buffer, public, returns true if we have successfully received the sequence number previously bool exists, UNT16T sequence, const, your logic here, check if entry exists and isn't stale return, buffer, sequence % size, equals sequence, return true, stub for compilation, comma 1, generate ACK bits, sender side logic, comma, local ACK is the highest sequence number we have received from the remote so far. We look back 32 steps into history to see what else we have. UNT32T generate ACK bits, UNT16T local ACK, const received packet buffer and received buffer, UNT32T ACK bits equals 0, iterate 32 times for the 32 bits in the integer for, UNT16T I equals 0, I, 32, plus I. Calculate the sequence ID for this bit position. Bit 0 checks, local ACK 1, bit 1 checks, local ACK 2, comma note, UNT16T underflow handles the wraparound, 01 equals 65,535, automatically UNT16T sequence to check equals local ACK, I plus 1, if we have received that packet, flip the bit to 1 if, received buffer exists, sequence to check, ACK bits equals, 1, I, return ACK bits, comma 2, decode ACK bits, receiver side logic, comma input, the header data from the incoming packet output, a list of all packet IDs confirmed by this header std, vector, UNT16T, decode ACK bits, UNT16T remote ACK, UNT32T remote ACK bits, std, vector, UNT16T, ACK packets, 1, the ACK variable itself is an acknowledgement of that specific packet. ACK packets pushback, remote ACK, 2, iterate through the bitmask to find previous ACKs for, UNT16T I equals 0, I, 32, plus I, check if bit I is set, 1, if, remote ACK bits an, 1, I, reconstruct the sequence ID based on the bit position. Bit 0 equals remote ACK 1, bit 1 equals remote ACK 2, automatic underflow handles wraparound. UNT16T ACK sequence equals remote ACK, I plus 1, ACK packets pushback, ACK sequence, return ACK packets. How to use this in your flow. Here is how you plug these functions into your main network loop. C++ void on send packet, packet header and header. We are about to send a packet. Let's tell them what the latest packet we saw was. Header ACK equals my client last received sequence. Let's also tell them about the 32 packets before that one. Header ACK bits equals generate ACK bits, my client last received sequence, my client received buffer, void on received packet, const packet header and header. They sent us a packet. Let's see which of our sent packets they are confirming. std, vector, UNT16T, confirmed params equals decode ACK bits, header ACK bits, 4, UNT16T. The following, confirmed params, mark this packet as delivered in our outgoing buffer. My client sent buffer mark as ACK. The following, important implementation note on UNT16T. In C++, UNT16T arithmetic is guaranteed to wrap around modulo 216. If ACK is 0, and you do AC1, you get 65,535. If AC is 0, and you do AC, I plus 1, where I is 0, you get 65,535. This is exactly the behavior you want for a circular sequence buffer, so no special if. Result, 0. Logic is required inside these loops. Would you like the code for the sequence buffer class next? Specifically how to handle the sliding window to ensure exists as O1? Code in C++ sequence buffer class next. Specifically how to handle the sliding window to ensure exists as O1. His is the critical data structure. As Fiedler notes, if you simply use a hash map, you will likely suffer from memory fragmentation and slower lookups. The sliding window trick here relies on using a sentinel value. We use a UNT32T array to store UNT16T sequence numbers. This allows us to use 0xFF, max UNT32 represent empty does not exist, which is a value that a valid UNT16T packet sequence can never equal. The C++ implementation. C++ include xtint, include vector, include C-string for memset, include cassert, helper to handle wrapping, e.g., is 0 is greater than 65,535, bool sequence greater than, UNT16T S1, UNT16T S2 return, S1 S2 and an, S1, S2 equals 32,768, S1, S2 and S2, S1, 32,768, template, type name T, class sequence buffer, public, size must be a power of 2 for fast modulo static constant size equals 1024, sequence buffer, reset, void reset, fill sequence array with 0xFF, sentinel for empty, we use UNT32T so we can store a value that is not a valid UNT16T for, int I equals 0, I, size, plus I, m entry sequence, I, equals 0xFF, comma assuming T is a POD, plain old data, type, we can zero it if T has a constructor, you might need a loop here memset, m entry data, 0, size of, m entry data, m first entry equals 0, comma O, 1, check, does this specific sequence exist in the buffer, comma bool exists, UNT16T sequence, const, int index equals sequence percent size, return m entry sequence, index, equals sequence, comma O, 1, lookup, get data if it exists, comma T find, UNT16T sequence, int index equals sequence percent size, if, m entry sequence, index, equals sequence, return and m entry data, index, return nulter, comma O, 1,